In this video, we're going to talk about financial models. So if you want to learn how to make it rain, keep watching. So the first thing to know is something that we call the simple interest formula. But before we even talk about that, we have to understand what interest is. So interest is the money that you pay for using money. So when you borrow money from a bank or a lending institution, that's called the principal. So the interest that is gained on that, you have to pay back to the bank or your lender. And that is determined by the rate of interest, or the interest rate per year, or however often they collect interest from you. So the simple interest formula is I equals P times R times T, where I is the interest money created, P is the principal, R is that interest rate, and T is the time that the money is invested or borrowed, typically in years. And this is especially useful if you are anything like Drake. If you've got a really big team, they need some really nice things. And you're going to need to understand simple interest and other types of interest in order to keep that money coming in. So you can, in fact, get them some really big rings and some really nice things. All right, some basic payment periods here and some vocabulary that is really important to know so you don't trip up with your decimals or your fractions when you are calculating interest rates. So there are 5 major payment periods. There are other types, but the 5 most common is something that we call compounding, which we'll get to in a moment, either annually, which happens over 1 year, quarterly, which, as it sounds, happens 4 times a year or every 3 months, monthly, obviously, 12 times a year over 1 month. Daily, which is kind of rare, but we see it. It's usually 365, although most banks use 360. And then semi-annually, which this chart left out, but that is half a year or every 6 months, which is 1/2 as a fraction. So if I take a look at this example that says a credit union pays interest of 2% per annum, which is really just per year, and it's compounded quarterly. If $1,000 is deposited and the interest is left to accumulate, how much money is in the account after 1 year? So essentially, I just want to know how much money I'm going to have in the bank after a year using this kind of interest model. So I'm going to start off with my I equals PRT, which is my simple interest formula, and I'm going to plug in what I know. So I equals, my original principal was 1,000, and then the rate that it happens is 2%, and that's 0.02 as a decimal, and then it's compounded quarterly, which means 1/4 or 4 times a year. And when I multiply that all out, that's $5. Now, that does not mean that I have $5 in the bank after 1 year. That just means that in the first quarter, I have added $5 to my 1,000. So that means I have to go in and do this for every quarter. So now I've calculated it for the second quarter, and instead of this 1,000, I have 1,000 plus 5, or $1,005 as I start the second quarter. And now I've gained another $5.03. So I'm going to add this to find out the third quarter. All right, so I've calculated that, and I've gained an extra $5.05 for the third quarter. And finally, let's calculate for the fourth quarter. All right, and I've calculated that to give me an extra $5.08 for the fourth quarter, bringing me to a total of $1,020.16 for the year. All right, so if that seemed somewhat exhaustive and slightly annoying, that's because it is. And we've actually found an easier way to calculate compound interest, and that is through this formula right here, where A is the amount accumulated over time, P is that principal, R is our interest rate, and N is our compoundings per period, so over a certain amount of time, and then T is our number of periods in that given amount of time. So if it's quarterly and it's over a year, there's 4 of them in the span of 1 year. So that's 4 and 1. And if we look at this basic graph over here, over time, our money increases with compound interest quite exponentially, one would say. It creates a curve. And with simple interest, it kind of just as a linear function over time. So obviously compound interest, if you're looking to make more money, which, I mean, pretty much everybody and the president is, am I right? Compound interest is the way to go. Something else that's really important is something called continuous compounding. And that is essentially when you earn interest on top of interest. So it's this continuous earning of interest over time. So the way that we represent that is this equation here, where A is going to be our amount of money after a certain amount of time, usually in years. P is the original principal. I spelled that wrong. And we use E here because it is that nice exponential rate, because if you're going to continuously compound something, it's going to grow at an exponential rate. And this is also something that we see in exponential growth and exponential decay, where R is our interest rate and time is time, usually in years. There we go, that's better. All right, so speaking of interest, there's this thing called effective rate of interest. So that means that it's the equivalent annual simple interest rate that would yield the same amount as compounding however many times a year after a full year of gaining interest. So the way that we look at that is we have R, sometimes it's written as R base E as in parentheses 1 plus I, sometimes that's represented with an R. So that's just the simple interest rate over N, which is the number of compounding periods, as we've seen before. And we also see the N up here. And then we take away 1 from that. And that will calculate the effective rate of interest. So the best example of that is, let's say you want to buy a CD, which is a certificate of deposit, from one of 3 banks. Let's say you've got American Express, First Internet Bank, and Discover, and they want to charge you a certain annual interest. So American Express has 2.15% compounded monthly. First Internet Bank is 2.20% compounded quarterly, and Discover has 2.12% compounded daily. So I'm going to plug that into the equation that we saw on the last slide for each of these and see what percentages turn up. All right, so when I calculate this out, this 2.15% interest ends up here as a decimal, and it's compounded monthly, so it's going to happen 12 times. That's why those 12s exist there. And then for the First Internet Bank, this is my percentage. It's happening quarterly, so 4 times a year, so that's why my 4s show up. And then Discover is doing this 2.12% here daily, so we use 365. And so when I look at these percentages, I'm going to look for the highest one because I want something that's going to kick back the most interest for me over a period of time. So that means that this one wins, so I'm going to go with First Internet Bank. Something else that we talk about in financial models is something called present value. So present value is what it sounds like. It is the current value of a lump sum of money. So we can represent that in 2 different ways, depending on the kind of interest model we're going for. So the first one is this one up here, which starts with our present value. How much is this lump sum of money worth? And that's going to be equal to the amount that I am hoping to have after T years, and that we put into 1 plus R over N, where R is our annual interest rate, compounded N times in a given year, and it's all to the negative power here. So negative N, which is the number of times it's compounded, times the number of years. Or if I'm going to compound this continuously, so I'm earning interest on interest on interest, I'm going to use this simplified equation here with E, which we've seen already this video. So if I take a look at a really quick example of present value, I have a bond that can be redeemed in 10 years for $1,000. How much should I be willing to pay for it now if I want a return of either 8% compounded monthly or 7% compounded continuously? So for the first one, I'm going to plug that into my first equation. So when I plug all of that in, my $1,000, which is what I'm hoping to get out of it, and then my 8% compounded monthly, which is my 12, and that 10 represents that 10 years here, and I plug that in, and I should expect to pay about $450.52 for that bond right now. So now let's check out the other equation if I want to do 7% compounded continuously. So when I plug in all of my information, I still have my $1,000, which I'm hoping to get out in 10 years at a 7% interest that's compounded continuously, because I have to use my E. It's going to cost me about $496.59 to get that today. So let's finish up with one last situation that is pretty common and pretty useful. So let's determine how long it would take to double an investment if it earns 5% compounded continuously. So I know that I have to use my compounded continuously formula, which is A equals P times E to the RT power. And I don't actually need to know the amount of money I'm working with either in the A or the P part. So what I do know is that I want to double my initial investment. So if my principal, which is my initial investment, is P, then that means that this A is going to be twice that, or 2P. So I can use my E here. So my rate is 5%, so 0.05, and then that's going to be times some value T. I'm going to simplify both sides here because I can knock out a P. So I have 2 equals E to the 0.05 T. Now, what I know about E, when I think of E, I have to think of ln. So I'm going to apply ln to both sides. And I know that that ln cancels with that E, so I'm given ln of 2 is equal to 0.05 T. And I'm aiming to find T by itself, so I divide by 0.05. So when I plug ln of 2 divided by 0.05 into my calculator, I get roughly 13.86. But if I'm thinking practically, it's going to take me about 14 years to double my investment. And that's going to do it for this video. Thanks for watching.